Swayam Prabha. Digital India. Educated India.
Okay, so in the previous class we were discussing about particle turbulence interaction. Specifically, I talked about the preferential concentration effect or preferential accumulation of particles in turbulent flows, which happens when the particle relaxation time and the time scale of turbulence matches. Now, in continuation of yesterday's discussion, what happens when we have polydispersed particles, that is particles of different size? How do they cluster? In case of clustering of polydispersed particles, each size class prefers different ED scales. So now what does this mean? So if you see, if we have a given particle size, then that determines the particle relaxation time. So now the ED time scale for which these two are similar, for that ED, the particles will accumulate around that ED, you can say that. Okay. Now, this means that if I fix particle size, I can fix the scale of the turbulent ED over which clustering is expected. Now, if we have particles of different size, then you can imagine they will cluster around EDs of different length scales. So, a smaller particle, if a smaller particle would be preferentially accumulating over a smaller ED, a larger particle will have the same effect for a larger ED, and so on. Now, the question is, if we have polydispersed suspension, do only a subset of sizes cluster strongly? Out of, now let us say this is your size distribution, out of this, is it like, let us say, only certain particles would show clustering effect? Is it the case? Next thing is, do clusters of different sizes overlap spatially? As I said, each particles of a given size would cluster at around a typical ED size or around a typical ED. Now, we can have those typical EDs defined for individual particle sizes. So now, if I have all particles together, can we simply superpose the features, or this plus this? Let us say if I have, let us say, bidispersed distribution, that is I have the size distribution say like this. Okay, only two sizes are present, and we know that the ED size for which they will cluster. Now, if we have them together, do we expect the cluster's size also bidispersed? Does this mean that we will have two different kind of clusters, one corresponding to this and the other corresponding to this? This means that it's a superposition of the effect. Or is it possible that clustering due to one particle size somehow induce clustering in the other particle size? Then if that is the case, if that happens, then we cannot treat this as superposition of the clustering effect for individual particle sizes. Okay, and actually that is the case. Okay, we don't see clusters of means discrete clusters like this if we have polydispersed effect. And then other questions also comes up. Does this promote particle-particle collision? That is, if we have preferential accumulation, especially for particles of different size, simultaneously if this effect is present, then can it promote collision? Now, why should it promote collision? Because we can expect clustering for some particles while the other particles won't show that effect. This means that we will have higher relative velocity between particles. So, particle to particle relative velocity is expected to be higher. So, that may promote collision. Now, as far as studies using polydispersed particles are concerned, they are relatively less compared to what we discussed earlier. So, the previous results that I had shown earlier, we had very narrow distribution of size or monosize distribution or monosize particles. In case of numerical simulation, you can strictly keep monosize particles, but in case of experiments, it is difficult to use. So, you can use a size distribution with a very narrow band of particle size. So, all the results that I had shown earlier corresponds to monosize particles. Now, here spray based studies refer to, means inherently in case of a spray, you have broad distribution of particle size in most of the sprays. So, those studies which use sprays, they have this effect present. Now, broadly there are two types of spray based studies. One is spray laden flows and the other one is sprays. Now, let us understand what is the difference. So, in case of spray laden flow, as you can see here, we have, for example, we have a wind tunnel in which we keep some grids. Why the grids are kept? Imagine there are no particles initially. The grids are kept because this will influence the turbulence characteristics. So, this is a conventional way of generating turbulence in a wind tunnel. The large eddy length scales would scale with the size of these meshes. Okay. Then what we can do is we can keep the mass flow rate same and change the mesh size or use different grids to realize different turbulent intensity in the wind tunnel. Okay. But actually in this case, we generate decaying isotropic turbulence. So, far away from this grid, the turbulence will be isotropic, but that will be decaying spatially. That is, as you move downstream of the wind tunnel, the turbulence would decay. Now, in this case, people have used single or multiple nozzles or injectors, as you can see here, which generates the spray, and this spray droplets are transported in the wind tunnel. And people have done experiments in this kind of flow configuration to understand clustering or preferential accumulation of particles. So, lot of experiments have been done. Now, on the other hand, you look at a spray. So, here also you have sprays, but this is called spray laden flow because as such there are no effect that is present in an actual spray. What effect we will discuss. But in both cases you have size polydispersity present. But what happens in case of a spray is that it has some unique features, that is, the spray entrains air from the surrounding to conserve momentum always. And in this case, the entrained air is always turbulent. Now, that air disperses the particles present in the spray. So, what do you understand with this? That it is inherently two-way coupled. You have the air flow or air motion due to the motion of the particles. So, in this case I have a stagnant ambience, But even otherwise, even if there, let's say there is a flow of air around it, still that air will be also entering into the spray. Okay. So we have this inherent coupling between the two phases in case of a spray. Now, how does this make this scenario different? Is that in case of spray laden flows, you can control the mass loading ratio, that is the ratio of the mass rate of injection of particles to rate of injection of the carrier phase. You can control this such that you vary this parameter mass loading ratio at the same airflow rate. So I keep the airflow rate same, I use more and more number of nozzles such that the mass loading ratio increases. That is possible. Okay. And in this case, we can create a situation such that it is one-way coupled. Because if the loading remains below certain level, it is one-way coupled. But that is not possible here. And also in this case, in spray laden flows, we can have a situation where we have one-way coupling, okay, or two-way coupling, but we have single phase counterpart also. That is, if I don't put particles, how would be the turbulence? Okay, that you can measure. Just stop the nozzles, you will get the single phase flow. Because in this case you can decouple the particle phase and the carrier phase. So it is possible that we have a flow without particles and flow with the same particle, and you study what effect the particles does to the flow. But in this case it is not possible to create such flows, because the airflow is created because of the spray itself. So this is not possible here. Although if you move quite downstream of the spray where the loading is low, locally you may have one-way coupling. Okay, because far downstream of the spray, the entrainment rate would reduce. So that can be considered as a one-way coupling flow. And this is what makes understanding clustering in sprays more difficult. So along that direction, I will show some results based on the studies that we did in this air assist injector. So air assist injector means it receives air from one side and liquid, in this case water, from the other side. And this creates a spray, as you can see here, and the measurements are taken downstream, far downstream of the injector. So the particle image velocimetry images of the spray droplets were captured, and the Voronoi analysis was used to identify and characterize individual particle clusters. As you can see in this image, this technique provides us individual particle clusters, and we can, once we identify individual clusters, then we can find the geometric parameters, for example area, length scale, perimeter, and also we can calculate the local particle number density. How many particles we have per unit volume, local density, and which is expected to be higher compared to the global density because particles have accumulated there. We will look at these techniques in more detail when we discuss the application of experimental techniques in multiphase flows later. Also here we can define the degree of clustering, or what is the extent of clustering, which way we can quantify that. That also is provided in this approach. Okay, so the injector was operated for different operating condition. As you can see, the liquid mass fraction, or this is basically the mass loading ratio, you can say, that changes. So you operate the injector such that the overall liquid mass fraction, the global liquid mass fraction changes. Now why I am showing this slide is to give you an idea of what happens in reality in particle laden flows. What does that mean? That means, so in this case we measure the particle size. So here you can see the, because this is polydispersed, we have polydispersed droplets, we have to define different characteristic sizes. If we define only one size, for example, arithmetic mean diameter, it may not represent the situation correctly. So here you see, so this is the arithmetic mean diameter, this is the Sauter mean diameter, which is nearly 2 times the arithmetic mean diameter. So if you do analysis of your results only based on arithmetic mean diameter, it may not give you the correct picture. Why? Because the difference in particle size, and not only that, if you calculate the Stokes number will increase by 4 times if you use SMD instead of AMD. Now you remember that you cannot define Stokes number based on a single size. You have to define some characteristic size only in this case. And here it is defined based on AMD and SMD. So you can see the difference here. Now, in this case, the Stokes number was calculated both based on large AD scale. So you see that Stokes number based on AMD is about 0.1 while SMD is about 0.2. So this means that they respond well to the large AD fluctuations. Okay. We may not say that they are perfect flow tracers because it is not very low, but still they show good response. That's what we can say. But now you look at the Stokes number based on Kolmogorov scale. So Stokes number based on Kolmogorov scale is now much larger. So what does this mean? This means that the same droplet show poor response to the small EDs. Okay. One more thing, now you see the Kolmogorov scale and compare it with the particle size. So what you see here is that the Kolmogorov scale is larger than the characteristic particle size, but still it is comparable. It is not, we cannot consider the particle size to be negligible compared to Kolmogorov scale. They are comparable. Now this is an important implication when you do modeling. Let's say of the same flow, if you want to do a modeling, you have to keep in mind, because the modeling approach will differ significantly based on this factor. So what we see here finally is that, okay, the particle size is less than Kolmogorov scale. It is not negligible but comparable. The particle shows very much different response when they interact with large EDs and when they interact with smallest EDs. Okay. Then let's see some of the results. What do we see? Now, using this Voronoi analysis, we can measure not only the clusters, as you can see here, but also the voids. So the voids are the entities which are devoid of droplets, or where the number density of droplets, we cannot say that it is completely devoid of droplets, but the number density is much smaller because the particles, in this case droplets, have moved away from the voids and they have gone and accumulated in the clusters. Okay. So, the characteristic size of the voids can also tell us about the physics of the problem. Okay. So, we can measure that. But what is interesting here is this plot. So, here you see, let us say you consider only the red line here, which shows the typical scale or length scale of particle clusters or droplet clusters in this case. Now, the length scale of the clusters are normalized with the large ED length scale here and normalized with the Kolmogorov scale here. So, on the same plot you can see. So, now what do you see? You see that you have clusters present across the turbulence spectrum. You have clusters with scale with Kolmogorov scale. For example, here you see. So, this cluster size is about 5 times the Kolmogorov scale, and the peak cluster size is about 10 times the Kolmogorov scale. Now, if you see the corresponding values here, this is of the order of 10 to the power of minus 2. So, that is 1% of the large scale EDs. So, the peak cluster size scales with Kolmogorov scale, but it is much smaller than the large ED scale. So, this means that clustering is strongly influenced by the small scales here, and that is also expected because the Kolmogorov scale was of the order of 1. Okay. But this is not equal to 1. Why? Because the Kolmogorov scale based on the Stokes number based on the Kolmogorov scale, see, was about 4 when you use AMD, and it was about 10 when you use SMD. So, now this means that these particles would scale at some EDs which are larger than Kolmogorov scale, where the Stokes number would be close to 1. Are you getting it? So, the size of the ED, okay, for which the Stokes number will be around 1, will be larger than the Kolmogorov scale, because the time scale of those EDs will be larger than the Kolmogorov time scale. So, that is the reason why we see clustering is happening, say, somewhere here. But still the influence of small scale EDs is there. But you still see droplets which are also scaling with the large EDs. So, this means that you have large scale clusters present also. Their number, their probability may be less, but they are present. So, finally, what we see here is that the droplet clustering in space is a multi-scale process. So, it is a multi-scale process. The clusters are present across the turbulence spectrum. They are not restricted to any particular size. Okay. And another interesting effect what we see here is that, as I just explained, clustering occurs even if Stokes number is much greater than 1. It can happen because particles cluster at some scale larger than the Kolmogorov scale, where their Stokes number is nearly equal to 1. You can interpret it this way. And also we see that the degree of clustering, as I had shown earlier, so this is a parameter which shows the strength of the clusters, strength of the clustering process. And this slide, this plot shows that it usually increases towards the edge of the spray. In this spray, in this scenario, okay. And also this varies with the particle loading. So, as the particle loading increases, the degree of clustering more or less increases. Okay. Then the number flux was calculated. So, what is number flux again? It is the number per unit area per unit time. Okay. So how do you calculate number flux? Number density. If you know the number density and if you know the particle velocity, in this case, okay, this is represented by u. U is the particle velocity here in this example. So flux is a vector quantity. So this number flux represents here actually the axial flux. So because we can count the number of particles in each measurement area, we can at any instant of time, we can find the number flux, the instantaneous local number flux. And then you average that over time and then you get this. So this represents the average number flux. Now, if you just write, just use Reynolds decomposition, then we can show that the average of the local number flux is basically equal to product of the mean number density and mean velocity plus this term. Now what is this? These are actually the correlation between fluctuations of particle number density and particle velocity. Okay, so here, okay, so this n represents the fluctuations. And now this parameter was calculated and you see this parameter was found to increase towards the edge of the spray, and we have just seen that towards edge of the spray, as you move from the core region towards the edge of the spray, the degree of clustering also increases. So as the intensity of clustering increases, the magnitude of this parameter is also increasing. So this indicates that clustering effect causes this correlation to be stronger. So if you remember, I had discussed this. So due to clustering, we have local fluctuations of particle concentration, or here number density. Now here the number density correlates with the particle velocity. And interestingly, what is found that the magnitude here is negative mostly. Now this is also interesting. So this means that when we have large number of particles locally, then the velocity reduces. That is what is meant by negative correlation. Now why should that happen? If you have somewhere large number of particles accumulated, then their velocity is reducing. This means that clustering is affecting the local drag. Okay, so the local drag is basically affected because there are many particles around the droplet in a cluster. Okay, so this is an experimental verification of this effect. So these examples are given only to give you a flavor of what happens in case of particle turbulence interaction and some of the evidence that we see about their effect, the effect of particle turbulence interaction. Okay, so this is about clustering of particles or preferential concentration effect. There are many other effects that also we see due to the influence of turbulence on the particle. One such effect is crossing trajectory effect. So crossing trajectory effect basically refers to the case when we have mean slip velocity between particles and the carrier fluid. Example, due to gravity or the gravitational influence, which leads to particles cross through turbulent eddies instead of following them. So if we have effects like gravity, till now we didn't consider the gravitational influence. Even in the experiments, so how do you neglect gravitational influence in the experiment that we will see just after this. So, in those experiments, the gravitational influence was negligible. Gravitational influence will always be there, but its effect was negligible. So, now imagine you have a particle which is interacting with an ED. Now, as of now, what we discussed, this interaction basically depends on the Stokes number of the particle. Okay. But now, in addition to that, you have the gravitational effect. So, the gravity itself will try to decorrelate the motion of the particles from the ED, and that will cause a mean slip velocity. Mean slip velocity means this. This is due to gravity. If you remember, in the previous class, I had shown you an example from a DNS simulation where they considered particles with Stokes number about 0.2 or so. That didn't show any clustering effect. But once you add the gravitational effect, you see a difference in the particle distribution. Okay, that is mainly because of the introduction of the crossing trajectory effect, where basically a particle crosses the trajectory of an ED. So, basically its effect is it reduces the Lagrangian correlation time of fluid velocity seen by the particle. So, basically because of this effect, if you calculate this correlation, it will be low because the particles are now not responding to the surrounding flow. And accordingly, this leads to different dispersion statistics. So, this is what we see here is only considering one particle, but if you have many particles, then it will affect the dispersion characteristics. And the parameter to understand the crossing trajectory effect is basically this one. So, here you calculate the mean slip velocity, the magnitude of mean slip velocity, and normalize that with the turbulent fluctuation. So, if this parameter is very low, then you can assume that the crossing trajectory effect are not present, otherwise they are present. Then the next one is gravitational settling. So, this is closely related to the crossing trajectory effect, but while the crossing trajectory effect can also be due to other effects, for example, external forcing. Somehow you force the flow, or the force is being, the flow is being forced by some other source. That can also cause crossing trajectory effect. Also, the difference in density of the fluid can also cause the crossing trajectory effect. But gravitational settling, okay, here we are referring to only the effect of gravity. So, basically in this case, the turbulence modifies the net settling velocity compared to Stokes terminal velocity in quiescent liquid. So, we know that if we release a particle in a quiescent medium, then finally it reaches terminal velocity, that is the Stokes terminal velocity. Now, the question is how that will be modified if we now inject the same particle in a turbulent flow. So, in this case also basically the mean drift velocity of particle relative to the fluid changes. Now, particle with preferential accumulation, particles which are under preferential accumulation effect, okay, they are dragged downward sweeping regions of turbulence, which leads to enhanced settling. This is also in the same example that I had shown. So, if you have particles here, then the side of the vortices or EDs, where the particle motion is along the gravitational direction, more particles are swept through that region or that side of the ED. Although if we have high turbulence intensity, it is possible that it will reduce the particle settling velocity because of the upward motion. So, anything is possible. So, to see the effect of the gravitational settling, we calculate this parameter. What is this? This is the terminal velocity in quiescent medium. So, you can calculate the terminal velocity and you normalize that with the turbulent intensity fluctuations, and if this parameter is small, then you can neglect the gravitational effect, and this was the case for the previous experiments that I had shown. Then there is another interesting effect which is known as turbophoresis. So, turbophoresis is basically referring to large scale migration of particles in turbulent flow due to gradients in turbulent intensity. So, this is a phenomena in which particle segregation or preferential accumulation happens because of the gradient in turbulent intensity. The particles move away from the regions of high turbulent kinetic energy to low turbulent kinetic energy. So, this happens when we have, for example, wall bounded turbulence. So, you have, see, in the previous cases we never considered any wall effect, but if you have any wall effect, then there is a strong gradient of velocity as well as a gradient of turbulent kinetic energy, and the turbulence intensity is high away from the wall but decreases towards the wall. Towards the wall, the turbulence intensity would decrease. So, the particles tend to diffuse more in regions of high fluctuations and less where fluctuations are weak. So, the particle diffuses more in the high turbulence region compared to the low turbulence region, and this causes an imbalance and the particles are drifted towards the wall, leading to preferential accumulation near the wall. And so, this turbophoresis velocity or the velocity at which this will take place, see, this basically depends on the gradient of the turbulent kinetic energy. Here there is no gravity effect. This happens because of the gradient and turbulent kinetic energy. Now, this is very important, for example, in aerosol deposition in lungs, dust transport in pipes. So, in all these cases, wherever we have the boundary effect or wall effect, this effect becomes important. Now, here you have to keep in mind that all these effects that we are discussing, they are not independent of each other. I mean, it may be possible that in the same flow, you have preferential accumulation as well as the gravity effect present, as well as turbophoresis present if you have a wall, as well as turbulence modulation that we are going to discuss now, that is also present. So, all can happen at same time. We are looking at the particle turbulence interaction through different aspects. We are understanding different aspects, but that does not mean that they are independent of each other. Okay, so now we consider turbulence modulation by particles. So, till now we discussed how turbulence influences particle behavior. Now, how particles influence the turbulence or the feedback from the particles. So, in this case, means inherently we have the two-way coupling scenario. So, we will look at this through some examples. So, first the effect of particle size. So, how particle size affects turbulence modulation. So, here you see the x-axis denotes the particle diameter to the length scale ratio. Here the length scale refers to the large D length scale, and these are from different experiments put together. And here you have percentage change in turbulence intensity. So, interestingly, what we see here is that when this ratio of particle size to the large D scale is about 0.1 or so, below that we have reduction in turbulence intensity. This means that small particles reduce turbulence intensity, while large particles increase turbulence intensity. So, this is positive, this is negative. Okay. Now, effect of particle loading. So, what happens if we increase the mass loading ratio, okay, or the particle mass compared to mass of the carrier phase? What happens if we go on increasing it? So, here you see in the left side plot, they have used particles of same size, 200 micron particles only, but the loading increases. Here the Z refers to loading basically here. So, the loading increases and they have measured the particle velocity also. So, this line, if you see this one, this line denotes the case of zero loading, that is single phase flow, and then they are introducing the particles and they go on increasing the loading. So, what do you see, that the turbulent intensity is reducing. So, when particles of size 200 micron is used, turbulent intensity is reducing. But then they conducted the same experiments. If you see, the Reynolds number remains same. This means that the turbulence or the turbulence without particles in the flow was same, but they used 3 mm particle or 3000 micron particle, 200 micron to 3000 micron. Now you see that the particle loading causes increase in the turbulence intensity. So, more or less we see the similar effect here, okay, as the previous case. Then effect of particle loading on turbulent intensity. So, yes, so earlier people only wanted to know what happens to the turbulent kinetic energy, but then some people also try to understand what happens to the turbulence intensity in different directions. Do they remain same? So, if let us say in one direction, in the axial direction, if you see reduction, then in the cross stream direction or radial direction, would you see the same effect? The answer is no. So, it depends on the direction also. So, for example, in this case, so this is also a wind tunnel based study. So, here you see the blue line refers to the streamwise direction. Streamwise direction means this direction, and this is the cross stream or transversal direction. So, streamwise direction, this shows the turbulent intensity, what happens to it. Okay, here they are plotting the kinetic energy or the inverse of turbulence intensity. Now, you compare this case with this case. So, there is a change in the upward direction. Okay. Now, you compare this case with this case for the streamwise direction. There is a difference. So, the change is now opposite, and same in case of so this is for low loading, this is for high loading, but in case of low loading, if you see this effect, blue to red and then green to this green, it increases. But now if you see here, blue to red, it decreases. Now green to blue, it is opposite. So, the point what I am trying to make here is that the modification in turbulence intensity in different directions may be different, and also it depends on the loading. You change the loading, this behavior can also change. Then this is interesting, that is effect of particle loading on turbulence spectrum. So, as of now we were considering the turbulent kinetic energy or turbulence intensity as a whole. We didn't look at the behavior at different length scales, but these authors, they tried to measure the turbulence intensity for different loading. So, what happens if you increase the loading, what happens to the small scale and to the large scale. So in this case, what they see here is that when they use particles with Stokes number 1.5, the turbulent kinetic energy increases if you are considering the small scales. This is Webb number. So this refers to the small scales. So at small scales, the turbulent kinetic energy has increased, large scale it has decreased. But you change the Stokes number of the particle, you see everywhere turbulent kinetic energy is reducing across the turbulent spectrum. Okay. So finally means what do we see overall? That it is very difficult to conclude what happens to turbulent kinetic energy, whether it increases or decreases. And if we go more detail, what happens to this behavior if we consider different directions, which refers to deviation from the isotropic behavior. And also what happens to this turbulence modification across the turbulence spectrum. So you see that it is difficult to arrive at a general conclusions. Why? Because of the number of parameters which govern this process. The particle size to the ratio of particle size to large d length scale, that is one parameter. Particle loading is another parameter. Particle Stokes number is another parameter. Okay. And also the Reynolds number of the flow, that is also another parameter. And also if you have some wall effect or if you change the flow configuration, then that has its own effect. So this is the reason why this study is complex. We'll discuss more about that in the next class.